Step on a scale and imagine the number simply doubles. Not because you gained anything, because the planet under your feet quietly gained a second version of itself, packed into roughly the same ball of rock. Every intuition you have says a planet that heavy should look dramatically different, twice as fat, twice as crushing, twice as everything. Almost none of that turns out to be true, and the parts that are true aren't true for the reason you'd guess. This isn't a purely hypothetical planet, either. It's a size class astronomers already study constantly, because rocky worlds noticeably heavier than Earth turn out to be common across the galaxy. Start with the part everyone gets wrong first: size. If you doubled Earth's mass and kept the same rock and metal recipe, you might expect the planet to swell to roughly twice the volume. It wouldn't. In 2006, planetary scientists Diana Valencia, Richard O'Connell, and Dimitar Sasselov modeled what actually happens to rocky planets as you pile on mass, and found that the radius grows far slower than the mass does, roughly by the mass raised to the power of 0.27. Do the math on a doubled Earth, and the radius comes out around 20% bigger, not 100. A decade later, Li Zheng, Sasselov, and Stein-Jacobson refined that model using the same seismic data that maps Earth's own interior, and the result held. Rock and metal don't inflate under extra mass. They get compressed. The added weight squeezes the interior into a denser package instead of pushing the surface further out. It's the same relationship astronomers now use in reverse. Every time a telescope finds a new rocky exoplanet and needs to guess, from its mass alone, roughly how big and how dense it probably is. That compression is the hinge everything else swings on. You'd expect gravity to double along with the mass. That's the whole intuition behind twice as heavy. But gravity at a planet's surface depends on both its mass and the square of its radius, and if the radius barely grows, that term barely shrinks gravity's growth either. Run the numbers from that same mass-radius relationship, and surface gravity on a double-mass Earth comes out around 38% higher, not 100. You'd feel it. A fit adult would suddenly be carrying the equivalent of a heavy backpack everywhere, all the time, standing up, sitting down, climbing every set of stairs, but you wouldn't be crushed, and you wouldn't be twice as heavy. The planet's own density is quietly absorbing the gap between what you assumed and what the physics actually delivers. It's a strange kind of consolation prize. The planet cheats you out of the dramatic doubling, but it cheats you out of the worst of it too. That extra gravity doesn't stop at your body. It reaches up into the sky. Every atmosphere thins out with altitude, and the rate it thins at is called the scale height. Essentially, how far up you have to go before the air pressure drops by a fixed fraction. Scale height depends directly on gravity. Pull harder, and the air can't spread as far upward before gravity drags it back down. A denser gravity Earth wouldn't get a taller, more generous sky. It would get the same air, if nothing else changed, squeezed into a thinner shell hugging the ground, thicker and murkier near sea level, and thinning out faster the higher you climbed. Mountains would poke through a proportionally thinner atmosphere than the ones you've climbed on this Earth, even standing at the exact same altitude, simply because the air above them has less room to stretch upward before gravity pulls it back down. Now put a body inside all of that. In 2018, physicists Nikola Poljak, Dora Klindzic, and Valencia Kruljac at the University of Zagreb modeled exactly how much gravity a human skeleton and muscular system could tolerate before locomotion itself breaks down, bones fracturing under standing loads, muscles unable to lift the body off the ground. Their answer, with the benefit of serious athletic training, topped out around 4 times Earth's current gravity, before circulation problems from blood struggling to reach the brain start setting real limits. Our 38% isn't anywhere near that ceiling. But it's enough to matter. Across the animal kingdom, the strength of a leg scales with its cross-sectional area, while body weight scales with volume. So as gravity climbs, the safety margin between what a skeleton can support and what it has to support keeps shrinking faster than either number does on its own. Nothing here would collapse. Nobody's legs would suddenly buckle underneath them. But standing, walking, and simply staying upright would all cost more energy than they do now, every hour of every day, for as long as anything stood on 2 legs or 4. Bodies built for this world would trend shorter and stockier over evolutionary time, not because taller bodies are impossible, but because they'd be paying a constant tax that shorter ones wouldn't. Here's where the honest science gets genuinely unresolved, not just complicated. You might assume a heavier, more Earth-like rocky planet would be even more geologically active than Earth. More volcanoes, more earthquakes, a livelier planet by every measure. In 2009, geophysicists Diana Valencia and Richard O'Connell modeled the mantle convection of massive rocky planets and concluded the intuition was backwards in a different way. Bigger rocky planets, they argued, should have thinner crust relative to their size, under more shear stress, meaning plate tectonics wasn't just possible, it was close to inevitable. But other research groups running comparable physics reached the opposite conclusion. Teams including Craig O'Neill and Adrian Lenardic, and later geophysicist C. Stein and colleagues, found that under different assumptions about how heat moves through the interior, the same increase in pressure could do the reverse, lock the crust into a single unbroken shell, a stagnant lid with no plate motion at all. Both camps are using real convection physics, running on real supercomputers, built from the same underlying equations. Neither has definitively won, and the gap between their predictions hasn't closed with time. If anything, more recent studies have only sharpened exactly where the two models disagree. That disagreement isn't just academic. Plate tectonics is the main reason Earth's climate has stayed survivable for billions of years. Subducting crust recycles carbon back into the mantle, and volcanism releases it again, a slow thermostat called the carbon-silicate cycle that keeps temperatures from drifting too far in either direction over geologic time. A rocky planet that's stuck in stagnant lid mode loses that thermostat completely. It has no reliable way to walk its own climate back from an overcorrection in either direction. You don't have to imagine what that looks like. There's already a planet next door running that exact experiment. Venus is close to Earth's size and mass, has no working plate tectonics, and sits locked under a runaway greenhouse hot enough to melt lead, with no mechanism left to recycle its own atmosphere back down. Nobody is claiming a heavier Earth would necessarily end up there. But it's the cautionary example sitting right in our own solar system for what a rocky planet looks like once its thermostat stops working. So the honest answer to, would a heavier Earth be more habitable, isn't yes or no. It's that scientists genuinely don't know which planet you'd end up with. One that recycles its own climate for eons the way Earth has, or one that locks in whatever climate it happens to have and never lets go, the way Venus already has. So picture that scale again, the number doubled, and picture what that number actually buys you. A planet barely any bigger, pulling roughly a third harder instead of twice as hard, breathing a thinner sky pressed closer to the ground, asking a little more of every bone standing on it. And underneath all of that, a coin flip nobody has called yet, on whether the ground itself ever moves again at all. Doubling a number on a scale is easy. Doubling a world, and everything that world quietly depends on, never is.